My master's thesis is focused on the Kotlin programming language, which is first and foremost a JVM language developed by JetBrains, but as we're going to see, it can also run on basically any other platform. Now, my thesis consisted of covering basically the entire language, along with some comparisons to other languages, first and foremost Java, and also covering the advantages and possible disadvantages of the language to see how it actually compares to Java and also some of the other newer languages. And in this technical talk, I will go into more detail about the language itself and basically do a comparative evaluation. So also cover how the language features of Kotlin compare to Java. First of all, I'd like to give a brief motivation as to why the Kotlin programming language might be interesting to look at. Now, first of all, we can see that the language is growing quite fast and now into the millions of developers that are actually using it actively, and it's still growing pretty quickly. But from a technical standpoint, what's more interesting maybe is that Kotlin can run on basically any platform. So first and foremost, you can run Kotlin on the JVM because it can compile or transpile to Java bytecode. But you can also run it in the browser, for instance, because it can also compile to JavaScript code. And it can even run on embedded systems or iOS using Kotlin native, which makes use of the LLVM infrastructure in order to cover native applications. And what's also interesting about this approach is that you can then share common code that can be used for all these platforms together. So basically having, for instance, some common library that can be used on the server as well as in the Android app or the iOS app or some web application using JavaScript or TypeScript. Now, apart from this versatility regarding platforms, Kotlin is also an interesting language with respect to its language features, which is what we're going to be focusing on in this talk. So I'm also going to be focusing on Kotlin on the JVM, the Java Virtual Machine. And we're going to look at some of the language features and compare those also to Java where possible. Now, basically, you can say that Kotlin just gathers the most interesting features from other languages. So you could say, in other words, it's deliberately uninnovative, so it doesn't usually create or test new concepts that haven't been proven or tested basically by some other language and are considered to be beneficial by the Kotlin team. So in this way, Kotlin then becomes a conglomerate of all the good features of other languages, or at least what the Kotlin team considers to be good features. And although there isn't much research yet on the Kotlin programming language, the few research that does exist seems to indicate that it does actually have benefits compared to Java. So this refers to code quality, but also to code conciseness. So basically saving lines of code to express the same kind of program. Okay, so much for the motivation. So let's now take a look at the philosophy of the language, and with this also at some of the most fundamental features of the language. Now, the first thing here is that Kotlin intends to be a safe language. So we're going to see that it focuses very much on immutability, which also goes hand in hand with a focus on functional programming. And it also provides null safety via its type system, which we're going to take a look at as well. Next, it intends to be a pragmatic language. So first of all, it's intended to be very toolable, which isn't surprising considering that it's actually developed by a tooling company. And it has language features like type inference, top-level declarations, and also a very strong standard library that all make it very effective to work with. So in the end, it's intended to be applicable for large-scale software because that's also what it's used for at JetBrains themselves. The next main point that Kotlin intended from the beginning is interoperability, because this is the only chance for a new language like this to actually be or to reach widespread adoption, because if it doesn't interoperate with the existing systems, then there's little chance for such a language to be adopted widely. So Kotlin first and foremost aims to be interoperable with Java on the JVM or for Android applications, but also with JavaScript and then also TypeScript, of course, in the browser. Also with C for native code and Objective-C for iOS and so on. So they're working on interoperability with other languages than Java as well. But in this talk, we're going to focus on Java. And last but not least, it focuses on readability, not just conciseness, because too much conciseness can actually then hamper readability again. And we're going to see some ways in which Kotlin achieves this. So let's now go through each of these points step by step and look at some example language features that actually enable these or support these points. So first of all, let's take a look at immutability. Now basically the most fundamental keywords in Kotlin, which are val and var to declare variables, already make this distinction quite clear because in Kotlin you have, well, these two keywords to create a variable. And if you use val, that's basically going to create a final variable, as you would say in Java. Whereas if you use var, then you can actually reassign this variable later on. Now this is quite a subtle difference maybe, but it's very important, I think, because in Kotlin you have the same kind of effort involved to create a read-only variable and a mutable variable. Whereas in Java, you have to actually, first of all, remember to, and then also actually have this kind of knowledge, and then also put in the effort to add this additional final modifier just to basically follow best practices, because most of the time, for instance, properties in a class should be final. Next, Kotlin differentiates very clearly between read-only collections and mutable collections in its standard library. So for instance, you have an interface list and you have a separate interface mutable list. So when you create a list of something, that's usually going to be a read-only list, and you can still create mutable lists if you want to, but in Java, you don't have any distinction like this. So you just have the list interface, and that actually refers to a mutable list and not a read-only list. And this has interesting implications also for variants of these types, as we're going to cover later when we talk about object-oriented features. But basically, when you have a read-only list, for instance, that just means you cannot add or remove elements or do any other kinds of modifications like this. At least if you're using pure Kotlin code, there's always a way to break this when you're interoperating with Java, because the read-only list from Kotlin has to map to some Java type when interoperating, and because Java doesn't differentiate, it basically just maps to a normal Java list, which becomes mutable again. So you have these kind of friction points always when you're interoperating. So that's why we say that they are read-only and they're not strictly immutable, because through interoperability, you can actually still modify them if you want to. But if you're using pure Kotlin code, you cannot actually modify any of those read-only collections. Now, the last point I want to mention here regarding immutability is that classes and members in Kotlin are final by default. So when you create a class or declare a class, for instance, you cannot create a subclass of it unless you explicitly declare that class as being open. So here basically Kotlin goes the opposite way than Java, because in Java everything's open by default and you have to explicitly add the final keyword to make it final. Now both of these approaches have their advantages and disadvantages. In Kotlin, because everything's final by default, it can make it harder to work with frameworks, for instance, which usually let you basically intercept with the framework by subclassing given classes. And that just doesn't work if they're all final by default. So if you're using a Java framework from Kotlin, that might be problematic, but there are then again tools that basically transform all the classes to being open, and that's just a workaround for this. But then again, on the other hand, the rationale for this in Kotlin is basically from the book Effective Java, so where it says if you allow overriding a class, you should design for it. And that's usually not the case in Java. People just declare a class and they don't really think about adding the final modifier. So then the class can be subclass, but it's not actually designed for that. And that can also lead to fragile code in some cases. So both these approaches have their advantages and disadvantages, and it's also, of course, a point for discussion. So at this point, I'd like to take a look at each of these features regarding immutability in the code to see how this actually turns out in practice. So first of all, very simply, you can declare a variable with the var keyword, and that just means you can reassign this variable later on, which also means you never really know what kind of value this is going to hold. On the other hand, you can use the val keyword, which means this becomes a read-only variable, and you cannot reassign this. The compiler would complain to you and give you a compile time exception just because it's a read-only variable. So this is the same as a final variable in Java. Okay, so next thing are collections. So here in Kotlin we have, first of all, again covering the pragmatic point, a very strong standard library. So to create a list, you can just do it like that. And that's going to give you an object of type list, which in Kotlin again is very much different from a mutable list, which would actually allow you to add or remove elements. And that's the one we're using down here. So here the type would then be a mutable list of int. And now for the normal list, for the read-only list, you cannot add or remove any elements. These are just not methods that are a part of this interface, whereas in a mutable list you can do that. All right, and the next point is final by default. So when you declare a class in Kotlin here, just like this, then you cannot actually create a subclass of this, which is done in Kotlin using this notation with a colon. And it's basically going to tell you to make this class open in order to be able to subclass from it. So you have to use the open modifier, and then you can create subclasses of this class. And the same also goes for any class members. So if you had any members in here, like some property, let's say, then by default, this is again going to be final. And we have to give this a value. So this is then going to be final again. So you cannot go ahead and say override val a of type string. And let's say this should have now a different value. However, if you declare this as open, then you can override it in the subclass. So this is again different from Java, where everything's open by default, and you would have to add the final keyword or modifier to be able to prevent overriding in a subclass. Okay, so let's go back to the slides. With this, we've covered how Kotlin favors immutability. So now let's take a look at how it achieves null safety. So basically here you can see that the Kotlin type system differentiates between non-nullable types, like a normal string type, and a nullable counterpart, which is the nullable type for this, like for instance a nullable string, which is denoted as string ? And you can see here that when you declare a variable of type string without the question mark, the compiler won't allow you to assign null to it. So this type can never hold a null value, whereas in Java, the type system, you could say, is flawed in this case, because null is considered to be an object of type string, but it doesn't actually conform to the string interface. So you cannot call toUpperCase or any method like that on it, and it's actually going to give you a runtime exception. So Kotlin's type system is more expressive here because it differentiates between these two actually distinct types, which are the normal string and the nullable string. In the code examples in the bottom left, you can see that in Kotlin, when you have an object of the nullable string type, you cannot just call a method like toUpperCase on it, because that might actually give you a null pointer exception. So the compiler won't allow this. Whereas in Java, it would be okay, but it might give you a runtime exception, at runtime. So it doesn't cover anything at compile time, it's just going to fail at runtime. Now in Kotlin, you can either use the save call operator using the question mark, like name $.toUppercase. What that's going to do is if the name isn't null, it's just going to call the method as usual. But if the name is null, it's just going to return null again as the return type of the entire expression. Alternatively, you could use the so-called unsafe call operator using 2 exclamation points. And this is basically an assert. So you're telling the compiler that you're asserting at this point that the name variable is not null at that point of the code, and that you're sure that that's the case. So it's basically just going to dereference the variable. And if you're wrong, if the variable actually is null at runtime at that point, you're going to get a null pointer exception again. So this is bad practice to use. Instead, you should use the safe call operator or just check for nullability beforehand. Okay, so let's take a look at this in the code again. Okay, so let's take a look at nullables. Now here you can see I'm declaring a normal string variable. So the compiler is just going to infer the string type here. If I explicitly define this type, you can see this is what the compiler infers, just because I'm using a string on the right-hand side. And you can also see I'm using a var, so I'm able to reassign this variable. However, I'm not allowed to reassign this to null because, well, null is not considered to be of type string. If I want to assign null to this, I have to use the nullable string ? as the type, and then it's no problem. I can actually assign null to a variable of this type, simply because null is part of the type string ? And down here you can see for the non-nullable type, I can simply call toUppercase on this, and this is always safe because the compiler knows that the string type can never hold null. On the other hand, for the nullable variable, I cannot simply go ahead and call toUppercase because that would be unsafe. Instead, I have to either use the safe call operator. So again, this is just gonna turn this in or return as the result of this entire expression null if this is actually null, and otherwise it's just gonna call the method as usual, or I can use the unsafe call operator. Okay, so let's go back to the slides again. We've now covered null safety, so now let's take a look at interoperability, again focusing just on Java and the JVM in this talk. So first of all, what interoperability basically means is you can use Java from Kotlin, so you can use any of the Java standard library or other external Java library classes in your Kotlin code. You could simply call local date.now or create a calendar object as you would expect. So just reusing all the many classes, libraries, frameworks that exist for Java. And the other way around, you can also use your Kotlin classes or any Kotlin libraries, frameworks that exist by now from Java. So here again, it's basically as you would expect. You can just use the class, call the methods on it. At least on a high level, there are some friction points again, which I'm not going to go into too much detail here. But you can find this in chapter 5 of the book that's part of my thesis. What's interesting to mention here is that there are some annotations that have the JVM prefix, which basically allow you to intercept or fine-tune the compilation process, so how Kotlin actually maps to Java class files or to Java bytecode to some degree. So you can, for instance, give a different name to a class or to a Kotlin file in the Java bytecode. You can say that some property is supposed to be static in the Java bytecode, or that it should be exposed as a field instead of having getters and setters. And these are just some of the ways in which you can basically fine-tune this compilation process. Now, one interesting issue that comes with interoperating with Java that I'd like to discuss here is that anything that comes from Java, so any object, any data that comes from Java, might be null. And now when you call something like local date.now, and you're using type inference here, the question is whether the compiler should now infer the local date as the type for this variable or a nullable local date. Now basically what the compiler does, it it infers neither of these. Instead, it infers a so-called platform type, which is denoted with an exclamation mark, so local date exclamation point, which means that this might be either nullable or not, and basically the compiler cannot decide this, so it defers this decision to the developer. So the developer now has to decide whether this method that they called from Java can return null or not. So the developer is supposed to know this, or at least make a judgment call. And of course, using the nullable type as the inferred type is always safe, but it's not as pragmatic because you have to deal with the nullability in your code. So in short, the compiler cannot always make the right decision here, so it decides to transfer the decision to the developer. However, you can help the compiler by using not null or nullable annotations in your Java code, and then it's actually going to use these and infer the corresponding type, so either the nullable or the non-nullable type. And just to exemplify that this can also be a bit more complex, if you're having generics or if you're using collections, like a map of integer to a list of string, then the compiler could infer all kinds of types for this, because the map might be a mutable map if it comes from Java. It might also be a read-only map, the list as well. The string could be nullable, the list could be nullable, the map could be nullable. So you have all these different degrees of freedom basically that also represent the additional expressiveness that Kotlin provides. So on the one hand, the distinction between read-only and mutable collections, and on the other hand, also the distinction between nullable and non-nullable types. And here it just becomes clear that in Java you don't have this expressivity. So one thing in Java might be many different types in Kotlin. So here also in the end the developer will have to decide what kind of type exactly should be inferred. Okay, so let's take a look at these features in the code as well. Okay, so first of all, just to show you, in your Kotlin code you can import any Java classes and then use them as you would expect. So you can also use type inference here again. And then you basically see if you autocomplete here, it's gonna show you the platform type local date exclamation mark. Now this is a special kind of type because you cannot actually use this type. You cannot declare a variable of a platform type, for instance. The compiler is just going to use this to communicate to the developer this kind of meta state where you don't know whether the type should be nullable or not. So here, for instance, the compiler uses the platform type to tell us that it doesn't know whether this should be a nullable local date or not. So we as a developer now have to decide what we want to do. We can also just keep it like this, use type inference, and then we're free to just call any properties and methods on it like this. But we might want to use a safe call operator or the unsafe call operator, but that doesn't make much sense. So the safe call operator, or we basically assume this is never going to be null, which would be a fair assumption for this kind of method call. And then we can just use it like this, or we could also, as a good practice, make our decision explicit at the point where we interoperate with Java. So we should already here say that we want this to be a non-nullable local date. So now we have basically communicated to other developers our decision that this should not be null, or that this method won't return null. All right, so let's go back to the slides. So now we've covered interoperability with Java, and that also concludes the basic features. So in the following, let's take a look at functional programming features in particular, and then also at object-oriented features. So first of all, for our functional programming, the most fundamental features that we need are lambda expressions, higher order functions, and lazy evaluation. In this case, we're going to take a look at lazy sequences in particular, which are basically the same as Java 8 streams. So let's start off with lambda expressions. So here in the first code example, we're using lambdas as well as lazy sequences. And actually, we're also using higher order functions already, but we're going to talk about them again on the next slide. So you can see we're calling a sequence, which basically enables lazy evaluation of these function calls. And on the right-hand side, you can see the equivalent Java code. So there we're using Java 8 streams, which is really the same concept. The only reason Kotlin reinvented the wheel here basically is because it wanted to make this available for Android development back when you only had access to Java 6 on Android. So you couldn't actually use any of these functional concepts yet. And Kotlin basically made that available to Android developers. But that's just as a side note. So the important thing here is that on the left-hand side in the Kotlin code, you can see we have this lambda syntax with curly braces. And we're not actually even using any parentheses on the filter function call, which is only possible because we only have a lambda as the only parameter of the function. So if the only function argument is a lambda expression, we can just omit the parentheses and basically get this kind of syntax where you just open up curly braces and, well, denote your lambda like that. And then also you can see we have this implicit variable called it. And this only works if a lambda expression only has a single parameter. Then you can use the it as an implicitly named argument. So you could also give this any name you want and then write an arrow similar to how Java does it. But you can also abbreviate the code and just use the it name. And this basically results in a nice syntax. So you can say filter it is active, map to it username, which is quite readable considering how concise it is. So really the concepts shown on the left and on the right for Java here are exactly the same, but the syntax is just a bit cleaner for Kotlin. And one interesting consequence of this kind of lambda syntax is that it allows to create or use type-safe builder DSLs, so domain-specific languages. This is a very constrained set of DSLs you can use, but it's also very easy to create, and it's just well built into the language, and basically just a result of some of the different language features of Kotlin. So this basically allows you to build complex objects with this kind of DSL syntax, like for instance here a user object where you can define a username, birthday, an address, and the address then is another nested object. And the way this kind of syntax is achieved is that these are basically just nested lambda expressions. But this syntax where you can omit the parentheses and where you can just nest the lambdas into each other can result in this kind of DSL-like syntax if combined also with extension functions and so on. So more details of this again can be found in my thesis itself. Now, before we jump into the code again, I want to also cover higher order functions first, just because these concepts are just so intertwined that it's hard to really show one of the two, or maybe it doesn't make as much sense to show one of the two without the other. So a higher order function, the concept is always the same. A higher order function is just a function that can either take in another function as an argument or return another function, or it might also do both. So it might take in another function and return another function. So we have an example here for a higher order function called twice, which takes in some function f, and it returns another function which basically just applies this given function f twice. And of course also these common functions like filter, map, reduce are also higher order functions, but these are already declared in the standard library. So concept as usual, but what's interesting in Kotlin is that you can inline higher order functions to avoid creating an object at runtime for each lambda expression that you use, which is how it works in Java. So you can simply use the inline modifier in front of a function, And that basically tells the compiler to inline the lambda that you pass into this function to each of the call sites. So when you call filter and you pass in, let's say, it is greater than 2, it will just inline the function body of this filter function into each place where the filter function is called. Now, inlining this piece of code into every place where it's used increases the bytecode size, which can be detrimental on embedded systems or even on Android. So it's usually better, or it's favored to use this for short functions. But of course you have this big advantage that you don't actually have any objects created at runtime. Or at least you don't have any, you don't have one object per lambda that you're using. And Kotlin also makes very heavy use of the inline modifier in its standard library. So all these common higher order functions like filter, map, also for each, they are all inline functions in the standard library. So let's go ahead and take a look at this again as a hands-on example in the code. So here we are. So let's first of all take a look at lambdas. So this again just recaps the syntax. You can declare a variable of type of some function. So here this is a function that takes in an integer and returns an integer. And you can declare an object of this type using a lambda expression. So because this just denotes a function, and this lambda takes in an argument of type int, just as you declared here, and it returns this number +1. Now what you can also do in Kotlin is you can make use of type inference, so you don't have to say that the argument here is of type int, because you already said that this is going to be a function from int to int, so the compiler can infer this. You can also do it the other way around and just let the compiler infer the type of this entire variable, which you could again define explicitly like this. But you don't have to if you say that the lambda takes in int and it returns the int +2, then the compiler can also infer that this function first takes an integer and then also returns an integer. And lastly, you can, for lambda expressions with a single parameter like this, you can make use of the implicit it variable. So just say it +2. All right, so that's it for the syntax for lambda expressions. So let's go ahead and take a look at higher order functions. So here we have this higher order function called twice that we also had in the slides. And you can call this function by just, well, passing in another function. In this case, a function that just adds 1 to its argument. So this entire expression here would return a function that performs this operation twice. So it will just add 2 to its given variable. So this would return 3. So that's just an example for a higher order function. Let's take a look at this Kotlin specific feature of inlining that doesn't exist in Java. So let's say you have a list of 1, 2, 3. Then Kotlin has a built-in standard library function called for each, which you can use instead of a normal for loop. And you can see that in the standard library, this function is actually declared as being an inline function. So basically this whole function body is going to be inline to each place where the function is called. So it's also going to be inlined into this place here. And we can actually see this if we go ahead and say show the Kotlin bytecode, and we can decompile this. And then we can take a look where this function call takes place. So here you can see that the for each, the higher order function for each, has been inlined into, well, in this case, a while loop. Now, just for comparison, I also created an own implementation called myForEach that basically does the exact same thing, but it doesn't have an inline modifier here. So if we call this function in the same way, you can see that if we go back to the decompiled Java code and scroll down again, you can see we had this inline function call here. But then if you use the same kind of function without the inline keyword, you can see it turns into a non-inlined function call that also uses a function object. So at runtime, this is going to create a function for the lambda. And just to show you that this can also look the exact same way, if we just add the inline modifier here, then you can see that both of these basically do the same thing. So here you have the first inlined function call from the standard library, and now our own myForEach loop also got inlined and is transformed to an expanded while loop without any function objects created at runtime. So that's it for this code example. Let's go back to the slides again. Okay, so with this we've covered functional programming features. So now as the last section in this presentation, I want to go through object-oriented features in particular. And here we're going to talk about special types of classes that Kotlin provides, having objects as first-class citizens in the language. And then last, we're going to talk about generics, in particular the concept of variance, and even more in particular the concept of mixed-site variance that exists in Kotlin. So let's start off with classes. So the first feature I want to mention here is just a convenience feature in Kotlin where you can use a data modifier in front of a class, and that's just going to give you getters, setters, hash code equals to string for free. It's also going to give you a copy method that allows you to easily copy objects of the type while also modifying some particular properties of the object. And it also generates component n methods. So for instance, in this case, these would be component 1, 2, 3, 4. And these are used by Kotlin in order to enable the feature of object destructuring. Now to make all this a bit more tangible, let's again take a look at this particular example in the code. Okay, so let's open up data class. So here you can see we have this data class address that has 4 properties: the street, the number, the postcode, and the city. And you can create objects of this class as usual in Kotlin. And then we can first of all take a look at the output of toString. So let me just run this code so we can look at the output of this function call. Okay, so here you can see that we have a standard implementation of toString given to us, which is just going to print the object as the class name and the properties along with their values. Now next we also have a standard implementation of equals. So in Kotlin, if you use a double equal sign, that's going to call the equals method. And if you use a triple equal sign, that's going to check referential equality. So you can see here that using equals, these two objects are the same. But using referential equality, they are not the same, of course, because they are two distinct objects. And we can also see that we have a working implementation of hash code. So if you create a hash set of these two objects that are equal, then the size of this set here is going to be 1 because the duplicates are removed automatically. Whereas if you use some normal class, so this person class here is not a data class, it does not have some working implementation of hash code. So if we create a set of two objects that are actually the same structurally, the size is going to be 2. So you can see this here, we have 1 and 2. And then we also have destructuring. So if we use an object of this data class, we can destructure it into its constituent properties in a single line of code. And we could also ignore some of these properties if we don't need them by just using an underscore. Okay, and lastly we have a copy method. So that's just going to give you a copy of the object and also allows you to override any of the properties if you want to. So for instance, moving the number in the street to some other address. And similarly, you could also change the city. So let's say city equals Berlin. So you can basically modify any of the properties you want. You don't have to modify any of them. but if you want to, you can. So this is a very useful concept or feature for things like data transfer objects and those kind of common data classes where you really just want to store some data, but they don't really carry much logic. Although you could also add methods to these data classes as usual if you want to. There are some limitations for data classes though, especially regarding inheritance, and you can read about them again in my thesis for all the details. So with this, let's go back to the slides and look at the next type of special class. So we've looked at data classes now, and the next one are sealed classes. So these are interesting because they basically give you more control over the class hierarchy, because if you declare a sealed class, then all its direct subclasses must be in the same file. And this enables the compiler to know that, okay, all the subclasses are in this file. So the compiler is aware of all the direct subclasses. So when you're using a when expression, for instance, like down there in the code example, and you cover these 3 different subclasses in your when expression, which is like switch in Java, then the compiler knows that this is actually exhaustive. So you don't have to add another default branch like you would have to in Java. And the compiler also knows that the when expression here always has a well-defined value. So you can also use this, the value of the expression as the return type of the evaluate function. And the compiler is not going to complain because it knows that there are only these 3 cases. So this evaluate function will always have a well-defined return value. And the same thing also works for enum classes, for enumerations. And seal classes actually can be seen as a generalization of enum classes. Because in enum classes, you also have your finite set of distinct elements, but each of those can only represent a single instance. And with seal classes, you basically also have your finite set of direct subclasses, of distinct subclasses, which are kind of like a partitioning as well. But each of those, again, represent a class and not just a single instance. So you can then have different objects for each of those direct subclasses. Like you can see here, we have 3 direct subclasses as data classes, from which, of course, you can create any number of objects. But in general, you can see that the compiler really makes use of all the information it can get from things like sealed classes, from things like nullability annotations, and all those kinds of things. So for this also, let's take a quick look at some of the examples in actual code. So let's go ahead and look at sealed classes. So this is just the same example in code. You can see the compiler is okay with this. We can just go ahead and let's create a main, because this is not a script file. And we could say print evaluate, create some expression like plus of a constant 1 and a constant 2. And you can see you can use these just as usual. You can also see we have the return value for this always well defined, because the when expression here covers 3 cases, and these are all that can actually ever occur. And just for sake of completeness, let's also quickly run this code. And you can see here we get 3 as the output, because we're adding 1 and 2. We could also make this an int here, but it returns double in case you want to also add division later on. Okay, so these are sealed classes. So now let's move on to objects as first-class citizens. Now there are 2 interesting ways you can use objects in Kotlin. So in Kotlin you have an object keyword, which is why I say that this basically makes objects first-class citizens. You can declare them, you can use them And there are two main ways you can use this. The first one is to create singletons. So you can just use the object keyword, just like the class keyword basically, to denote some object you want to have at runtime, which is really the same thing as having a singleton. Singleton is a class of which you just want to have one instance at runtime, and that is basically just an object. So the main advantage here of the Kotlin code compared to Java is that the object keyword represents the intention really well. You just want to have an object of this thing at runtime. The second way you can use the object keyword is in expressions. So these are basically Kotlin's way to basically replace anonymous inner classes in Java. So where you would use an anonymous inner class in Java, you just use an object in Kotlin. And you can see there that you can also define superclasses or implement interfaces using object expressions. So these are kind of similar to the normal class keyword, but of course they represent just a single object at runtime, whereas a class is kind of like a blueprint for objects. So let's go through a quick hands-on example for this in the code as well. Okay, so let's go ahead and check out objects. So here we have an example where we have some interface for a factory, a very simplified one that just defines a function create that returns an object of type T. And we want some person factory, which is a singleton, so we're just going to use object. Now this person factory object also implements the interface factory of person, and therefore it implements this function, it overrides the function, and well, as a factory does, it just creates an object. So this just shows how to use the object keyword for singletons, and the fact that you can also implement interfaces. You could also have a superclass here, and all this is possible with the object keyword. Okay, so this was just a quick example for object declarations. Okay, so much for objects as first-class citizens in Kotlin. So now let's get to the last topic I want to cover here, which are generics and variance in particular. So Kotlin here actually has kind of an innovative feature, which is quite unusual, which is called mixed site variance. They worked on this together with Cornell University, and it's basically a combination of declaration site variance and use site variance. So in order to understand variance, let's first take a look at declaration site variance. So here we have an example of a stack class, and in order to use declaration site variance, we can use two different modifiers. So we can either use out or in. And we can use these modifiers on generic type parameters. So here we declare a stack of out e. And this means that this class only produces elements of type e. So you can only have e as return values, like for instance in the peek function. But you cannot have a function or a method such as add, where you actually take in an element of type e, because this would then no longer allow covariance. So covariance is related to the out keyword, and it means that, for instance, a stack of int is a subtype of a stack of number. Now covariance is only possible if the stack only produces elements of type e. So this is why it needs the out modifier on e in order to be covariant. Because otherwise, let's say the stack has a method called add, as down there, you can add an element of type e. Then you could say, okay, I want an object of type stack of number, and I initialize that stack of number as a stack of int. This is okay because stack of int is a subtype of stack of number, since we're assuming a stack is covariant. But now if our stack has a function or method such as add element of type e, and we're using a stack of number, then we can add any number. So we could also call our stack.add, And now we have to pass in an element of type number. So we could pass in a double, but under the hood at runtime, again, we had our stack of int as the actual object stored here. So we're then trying to add a double to a stack of int, and that's going to fail at runtime. So this is why it is not safe to say that a class in general is a covariant. So if we had something like a mutable stack of e without the out modifier, and the stack has an add method, then it is not safe to say that the stack is covariant. However, since we're using the out modifier, we can only have e in so-called out position, so only as return type, meaning that the stack can only produce elements of type e. And in that case, it is safe to assume or to consider this type as being covariant. Now the reverse is true for the in modifier. So we're going to see an example of this in a minute. But if we have in, that makes the type or the class contravariant with respect to that type parameter. And that would then mean that, let's say our stack would be contravariant. Then the other way around, a stack of number would be a subtype of a stack of int. Now this doesn't make any sense for a stack, but we're going to see an example where this does make sense. Now one thing I want to mention here, because you might have noticed, is that we can still pass in elements of type e in the constructor. So that's what in the parentheses in the first line there, you can have constructor elements or a constructor argument where you get in elements of type e, because that is still safe. But once the object is created, you can then no longer accept or take in any elements of type e from the outside. You can only produce elements of type e if you're using the out modifier. Now, before we take a look at this in the code, I also want to quickly cover use site variance, because this is the only type of variance that Java supports. And Java supports this via wildcards. So in Java, again, a list might also be a mutable list because Java doesn't differentiate between those two interfaces. So in Java, a list cannot be covariant in a safe way. In Kotlin, that's okay. If in Kotlin you're using the read-only list interface, that interface is covariant. So that's why here in this example, we're comparing Kotlin's mutable list on the left-hand side to Java's normal list on the right-hand side. Now, again, in Java, you can say you want to use a list of extends number, which means you want to use the list in a covariant style. So by using this wildcard, you are then allowed to assign a list of integer to this list of, well, something that extends number. And you can do the same thing still in Kotlin. You could say mutable list of out number, and you can then assign a mutable list of int. Now in both cases, these assignments would fail without the out modifier or without using a wildcard in Java. So use site variance must be used also in Kotlin whenever declaration site variance doesn't work, basically. So not every class can be covariant or contravariant. Like for instance, a mutable list type has methods like get, which return elements of type e, but also methods like add, which take in elements of type e. So these classes just cannot be variant. They are called invariant. But for those, you can still use use site variance if you have a particular part of your code where you want to use those classes in a covariant or in a contravariant manner. Okay, so let's also take a look at these in the code. So let's take a look at covariance first of all. So this is just a quick example again for what contravariance means and how Kotlin or where Kotlin uses it. So if you use the read-only list interface in Kotlin, and if you can actually can also jump to the declaration, you can see it's a list of out e. So this makes this a covariant type. So we can now say we want a list of number and assign a list of int to this, and this is perfectly fine. The compiler will not complain. But if we try to do the same thing for the mutable list interface, this doesn't work, because again the problem would be that we could say mutable.add, and then we could add some number, so we could also add a boolean, but under the hood we would be using a mutable list of int, and then we end up at runtime trying to add a double to a list of int, and it would fail at runtime. So that's why Kotlin doesn't allow this in the first place. However, we could also say we want to use or make use of use-side variants. So we say mutable list of outNumber. What happens now is that if we try to say mutable.add, we get element of type nothing. So we cannot actually call this method. There is literally nothing we could add as an argument here, because the type nothing in Kotlin is quite special. It represents the bottom of the type hierarchy, and there's just no object that belongs to this type. It's completely empty. The nothing type, we cannot even use null or anything else. So there's no way to call this method, and this is why it is then again safe to use a mutable list of int for a mutable list of outNumber. And the same could also be achieved in Java by using wildcards like question mark extends number, for instance. Okay, so let's also take a look at contravariants as well, just to give a more intuitive feeling for this. So let's say we have a class hierarchy, a very simple one, with a vehicle as the superclass, and we have cars and trucks as subclasses of vehicle. Now we could declare a class repair shop of some type E. Now this type E should be some kind of vehicle, because we're talking about a repair shop, so there shouldn't be people or person objects coming in. And this is how you declare the upper bound for the generic type parameter in Kotlin. And then here it actually makes sense to make use of contravariants. And we're also making this class contravariant at declaration side, because it should always, it can be contravariant in general. We don't have to do this only for particular use sites. This works because we only take in elements of type E. So let's say we have a method called repair. We have a parameter of type E, but we don't have any methods that would actually return elements of type E, which wouldn't be allowed for contravariant classes. So what this then allows us to do is we could say we want some repair shop that knows how to repair cars. Now it makes sense that we can actually assign a repair shop of vehicles to this, because a shop that knows how to repair any vehicle also knows how to repair a car. So we can use this car repair to repair an object of type car, because this one actually knows how to repair any vehicle. So this is why here it makes sense that our repair shop of car, or rather our repair shop, let's do it this way around, our repair shop of vehicle is a subtype of our repair shop of car. So again, intuitively, that just means that a repair shop of vehicles in general knows how to handle objects, or knows how to behave like a repair shop of car. Now, one thing I want to mention here is that in the book Effective Java, Joshua Bloch basically mentions this abbreviation PEX, which stands for Producer Extends Consumer Super, which means that in Java you use extends something for producers, meaning for covariant types, and you use the wildcard super sometime, and you use this for consumers. So producer extends consumer super, and in Kotlin you can see that it becomes a bit more readable because of these modifier names in and out. So here you could basically say consumer in, producer out. So again, we have, first of all, a bit more conciseness, but more importantly, it's more readable. So the choice of modifier words is not only very concise, but also expresses the intention very well. Okay, so that concludes the code example here. So let's jump back into the slides again for a second. Okay, so with this, we've covered the object-oriented features of Kotlin as well. And with this, I want to conclude this overview of the Kotlin programming language, along with the comparison to Java in particular. Thank you very much for your attention, and any more details about the features mentioned here, but also many more features that didn't make it into this video for time constraints, all those can be found in my thesis itself with much more detail and many more features of the language as well.